Welcome to the 10th chapter of Multiply Dynamics using Alter HyperWorks Motion View Motion Solve. So in this chapter, we will take a deep dive into the constraints and mainly concentrate on the higher pair constraints. So now let me take you quickly through the different types of constraints available in Motion View Motion Solve. So we have the lower pair constraints. A lower pair constraint is basically an ideal joint that constrains the contact between a point, line, or a plane in the moving body to the corresponding line or a plane in a fixed body or another moving body. So these have physical analogies, and for example, a revolute joint can be correlated to a hinge joint. So then you have the joint primitives. They constrain combination of individual degrees of freedom between the bodies. In most cases, there are no mechanical equivalents for the joint primitives. Moving on to the higher pair constraints. Generally, a higher pair constraint is the one that requires a point, curve, or a surface in moving body to maintain the contact with a curve or a surface in the fixed body. Motion is a prescribed displacement, velocity, or acceleration on a body along a specified direction. When motion is applied on a body, the free degrees of freedom of the body are replaced by prescribed movement as specified by the motion. So thus, motion falls under the category of constraints. And the other constraints include the coupler or the gears. So here, they are used to specify algebraic relations between two or more joints. So as you can see on the screen, the classification of constraints, there are the various types of constraints available in Motion View, Motion Solve. And we've already gone through the lower pair constraint and joint primitives in the previous chapters. And in this chapter, we will be concentrating on the higher pair constraint. So we have the following higher pair constraints: the point to curve joint, point to surface joint, curve to curve joint, curve to surface joint, surface to surface joint, point to deformable curve joint, point to deformable surface, and a constraint meet. So let us start with the point to curve joint. So a point to curve joint is a higher pair constraint. This constraint restricts a specified point on a body, as you can see in the animation on the screen, to move along a specified curve on another body. So this hammer-like structure that you can see, it has a particular point that is resting on this curve and it is moving along. So the curve may be open or closed, planar or in 3D space. The point may be a rigid, flexible, or a point body. So this constraint can help in avoiding the 3D contact modeling, okay? Because the 3D contact modeling is very time consuming and it involves many complex equations. So you can use this particular point to curve joint in some of the cases to substitute the contact modeling. So it may prove advantageous since the proper contact modeling in many cases involves fine-tuning of contact parameters. And one good example for that is the knife edge cam follower mechanism. So in the left hand image, you can see a robotic arm. So this is another example of the point to curve joint. So and on the right hand side, it is there's an example of this hammer like structure moving along this particular curve path. So in the left hand side image, so this is the robotic arm trying to move along this particular curve that's been prescribed by the user. Okay, so these are some of the examples of point to curve joint. Now let's move on to the next slide. So this slide it gives us a brief description of the point to surface joint. A point to surface joint, also called as the PTSV joint, also falls under the category of higher pair constraint. This constraint restricts a specified point on the body to move along a specified surface of another body. Okay, so in this slide, you can see that this needle-like structure is, say, a body I, and this irregularly shaped structure is body. So it will allow this particular needle-like structure, the tip of this needle, to move along a particular trajectory on this body J, the surface of body J. So the tip of this body I moves along a prescribed path on the surface of body J. So in this case, we can define a point to surface joint. So the next one is a very important joint, which is the curve to curve joint. So curve to curve joint is a higher pair constraint. And it's a this constraint consists of a planar curve on one body rolling and sliding on the planar curve of a second body. So this constraint can act as a substitute to the contact modeling in many cases. Okay, so this will eliminate the complex formulations of the contact model and thereby making it much easier for the solver and also reducing the run times. So one such case is a CAM follower mechanism, so which is showed in the next slide. So in this case, the follower is in the form of a roller. So instead of modeling the contact between the CAM and the follower, we can specify a CVCV constraint between their curve profile. We can go on to the next slide. So here, one thing that you need to note is the curve-to-curve constraint removes 3 degrees of freedom from each of the systems. Okay, so when the body of the first curve, let's move on to the next slide. So when the body of the first curve is in space, the second curve is allowed to move in 3 ways. Okay, so say this is the curve profile of this roller is the first case. So in that, so consider when the body of the first curve is in fixed space, the second curve is allowed to move in 3 ways. It can slide along the first curve, it can roll along the first curve, and it can rotate above this common tangent that you have. Okay, if you have this roller in the form of a curve, the path of this roller in the form of a curve, and the path of this CAM as another curve, then you can see you have a common tangent between the roller and the CAM, right? So it can rotate about the common tangent at the point of contact. So these are the 3 degrees of freedom that are removed. So the curves can thus rotate about the common tangent at the point of contact, and therefore it can move out of the plane even when both the curves are planar. So I think this becomes more, this will be more clear to you guys when we do the exercise demo on chapter 10. Let's move on to the slide 8. So this is basically the curve to surface joint. This joint is used in very rare cases where the curved region with a very small thickness of a body A interacts with the surface of body B. In these cases, we use the curve to surface contact. It is basically the interaction of the 2D spline with the 2D plane. So now let's move on to the next slide, which is the surface to surface joint. So if we want to constrain the surface of one body with the surface of another body, this constraint can serve as a very good substitute again to the 3D contacts, which can increase complexity and so this will help in decreasing complexity and simulation time. So we can use this constraint to calculate the friction losses between the two bodies that have surface to surface interaction. Now moving on to the next slide, it is the point to deformable curve constraint. It's also called as the PT-DCV constraint. So it again falls under the category of higher pair constraint. So this constraint restricts a specified point on the body to move along a specified deformable curve on another body. The curve may be open or closed, planar or in 3D space. So the point may be a rigid, flexible, or a point mass. So we can consider the example of a long stick supported by revolute joint at both of its ends, and a ball or a mass is constrained to move along this particular stick with a PT-DCV joint, okay, with a point to deformable curve joint. So here what happens is this long stick can act as a slender beam, so that can be the deformable curve, and this point mass, it moves along the curve. So please note that this type of constraint does not always ensure that the contact point between the two bodies will always stay within the range for the specified curve. So additional forces at the end need to be defined by the user to satisfy this particular requirement. So if the contact point goes out of the range of the data specified for this particular curve, the solver encounters an error. So the solver is going to throw an error saying that this particular simulation cannot be converged. So in that case, one has to basically change the initial velocities for the ball, okay, or increase the range of the data specified for the curve, or run the simulation for a very short interval of time. So these are some of the workarounds that we can do to get this particular constraint running. Point to deformable surface constraint. So the point to deformable surface is a higher pair constraint that restricts a specified point on a body to move along a specified deformable surface of another body. So here you can consider the example of the ball or the mass, okay, on a sheet of paper, okay, that's constrained on two ends. So the sheet of paper acts like a flexible body on top of which the ball is resting. So if this constraint here is applied as and when the ball moves on the deformable sheet of paper, the z displacement of the ball can be calculated. So again, this can serve as a very good substitute for the 3D contacts involving flexible bodies. So that will be explained in the next chapter, wherein I cover the 3D contacts. We in motion view, we do not have the 3D contacts established for flexible bodies. So in that case, this particular constraint can serve as a very good substitute. So in this particular slide, we've tried to summarize all the constraints that we've studied so far. And you need to note that in the higher pair constraints, the two bodies are in contact at a point or along a line, and the relative motions of these coincident points are not the same. So this is just a summary of what all we have covered so far. So this slide here explains quantitatively the number of translational and rotational constraints that can be eliminated by using each of these higher pair constraints. Okay, so a point to curve constraint, it removes 2 translational degrees of freedom and 0 rotational degrees of freedom. So totally, this point to curve constraint has the ability to remove 2 degrees of freedom. The point to surface constraint can eliminate 2 translational degrees of freedom and 3 rotational degrees of freedom. So totally it can remove 5 degrees of freedom. The curve to curve constraint, it eliminates 2 translational degrees of freedom and 1 rotational degrees of freedom. So in total, it can eliminate 3 degrees of freedom. The curve to surface constraint can eliminate 2 translational degrees of freedom and 3 rotational degrees of freedom. So in total, it can eliminate 5 degrees of freedom. The surface to surface constraint can also eliminate 2 translational degrees of freedom and 3 rotational degrees of freedom. Hence, it can totally eliminate 5 total degrees of freedom. The point to deformable curve constraint eliminates 1 translational and 3 rotational degrees of freedom. So thus eliminating 4 degrees of freedom. And the point to deformable surface constraint totally removes 2 translational plus 3 rotational degrees of freedom. So in total removing 5 degrees of freedom. So this slide basically gives you the quantitative information on the number of degrees of freedom that can be removed by each of these higher pair constraints. So in this slide, I'll be explaining regarding the demo that we'll be doing in exercise 10. We'll be modeling a cam and then the follower. The follower is resting on this cam and it is attached to a follower shaft which reciprocates as cam performs its rotation. Okay, so this constraint again can act as substitute for contact modeling. So instead of creating a 3D contact between the cam follower and the cam, you can try to use the profile of this particular cam. You can capture that as a curve, a 2D spline, and also capture the path along which this cam rotates. You can take that path as another curve, and you can try to establish a curve-to-curve joint between these two profiles. So this totally reduces the runtime and also the complexities of the equations that are involved in formulating it. So this is something that we'll try to simulate in the exercise 10. Thank you.